Good morning and welcome to Advent of Code in F# day 17. I have nothing interesting to say about yesterday's puzzle, so we're going to be counting down live to the next puzzle. Here we go. Conway cubes. Conway cubes. That's an interesting combination. We're still traveling as our flight slowly drifts through the sky. The elves at the Mythical Information Bureau at the North Pole contact you. They would like to, let me quickly check if I put my audio on. Yes, you can hear me. Okay. So the elves at the Bureau contact us. They'd like some help debugging a malfunctioning experimental energy source aboard one of their super secret imaging satellites. Okay. Conway cubes, yeah. Pocket dimensions, interesting. So a pocket dimension contains an infinite three-dimensional grid. Oh, cool. We're going to do Conway's live in 3D. I love it. At every integer... Conway's game of life? Yeah, Conway's game of life in 3D. At every integer three-dimensional coordinate xyz, there exists a single cube. Yeah, which is active or inactive. This is Conway's game. Almost every cube starts inactive. The only exception to this is a small flat region of cubes, which is our input. Okay. The cubes in this region start in a specified state. Okay, so we get a 2D input, but our game or our world is like a 3D space. Energy source that proceeds to boot up by counting 6 cycles. That's not a whole lot of cycles. So we just play Conway's game of life in 3D for 6 cycles. Okay, gotta remember it's cycles because I always name it something else. Each cube only ever considers its neighbors. Yeah, so we have to do a 3D search of the neighbors. How many neighbors does it have? 8 plus 9 plus 9? Yeah, 8 plus 9 plus 9. That is 26, yeah, okay. Clear. Simultaneously, we've already seen this during the seed exercise, yes. Immutable data is a godsend for this. These are the rules we need to apply, so 2 or 3 remain active. Yeah, let's get to the rules when we start implementing them. Okay, so now we just have to run the game for 6 turns, yeah. So consider this as an initial state, then we do some ticks, and we name that Z for some... Oh no, Z is the... Oh yeah, Z is the 3rd dimension, so it's going to be hard to represent this visually. So this is how we start, and then after 1 cycle, it's spreading in 3 dimensions, and it's infinitely big, so the world keeps growing in 3 dimensions. It's crazy, I love it. So after full 6 cycle completes, this many cubes are left. Let's see how big our world is going to be initially. Oh, that's actually not that bad. What is it, 10 by 10? Something like that? It's not that bad. Oh, I haven't prepared my day 17 this time. Let's do that right now. Copy paste, copy paste. See a lot of people with a template. That's also a smart thing to do if you're going for the speed record, which we are not. We are here to learn and have fun. Where's my input? There we go. For some reason my input will not copy. Oh, come on. Yeah, there we go. 8 by something, okay. Let's get rid of, yeah, we don't need regular expressions today. Let's maybe keep a file read. We will be needing our input. And is it the correct input? Yeah, okay, we can get started. So I think this is the 31st time now that I implemented Game of Life, so it's going to be quick, but I like the twist that it's in 3 dimensions. Thinking about data structures, how will we represent our universe or our 3D world? I don't remember what I did last time. Did I do 2-dimensional arrays or a lookup table? don't remember. Let's do a lookup table. It won't be the most memory efficient or time efficient, but for a starting universe this small and only 6 ticks, it'll be more than enough. Part 2 will probably be a lot more than 6 cycles, or even finding some initial state so that a property holds. But yeah, let's not worry about the future. Let's dive in and let's use maps. So what do we need? What's our state? Oh no, maybe before we start thinking about state, what's our general strategy? We need to be able to cycle. So we need to give an initial input, what's the next state, and we need to be able to do this a certain amount of times. So we need something to generate a sequence, or something to generate subsequent cycles of the world. And that sounds an awful lot like an unfold again. So I'm going to try using an unfold or some recursion that would also work. And we definitely need to be able to parse our input. So let's start there. Let's think about how we represent our states. So each individual what's the name? So layer by layer, I see cycle. What's like a single dot in the state called cube? Okay, so let's call this a cube state. And what is it, active or inactive? Yes. Active. You can like leave the first pipe if you're defining a union type. And then it reads like a literal OR. So cube state is active or inactive. I like that. Let's write a parser real quick. Does it make sense? Yep, makes sense. And we are going to use a 2-dimensional array. No, we were going to use a map of 3 dimensions. Yeah, a map using a 3-dimensional coordinate as the key and the state as the value. That would be enough for part 1. Yes, that would be enough. So let's, what are we calling this? World pocket dimension. Let's call it pocket dimension. So single state of a pocket dimension in our case is just going to be a map of the coordinates. Will the coordinates change? Don't think so, and otherwise we're screwed anyway. And cube state. So this is our dimension, and let's now parse our input into a pocket dimension. So is it the, actually it doesn't really matter. I was thinking like z, what is z initially? Are we like somewhere near the origin? But it doesn't matter because we just, it's infinite anyway, and we're never talking about coordinates. We're just growing and morphing the world. So let's, for our implementation, let's assume that the given input is like z equals 0, just like the example. So we can parse our input. Yep. So input for line in input, because we will be needing the indices to put in our map. So let's call this a index thing again. And then for character in line, and let's also index that. And let's make our key value pairs. So it's x, y, z. X is the horizontal axis, so that means car. Let's call this a row, line, column, character, and row. Let's type that out a bit more. So x coordinate is horizontal, so it's column, y coordinate is the row, and the z initially is 0. And what do we get? Well, we get the character, and let's parse that. So let's write quick parser for the parse state given a character. So let's just do a function. Let's do a pattern match. if it is, what was it, dots, dot, what is that, inactive? Yep, dot is inactive, and Twitter symbol is active, and otherwise we don't know. So that's a parser for our state, and this is the pair we need to return, yeah? So this is a sequence, and I need a do instead of an arrow somewhere, I'm guessing, yeah. I'm still not like 100% comfortable with this for comprehension syntax, but it works. And this is now a list of these key value pairs, so we can just make this a map. I think we have our input parsed, and I was thinking, like, do we actually need to keep track of the like the inactive states? It's not necessary, but it doesn't hurt either. So let's go with it. If we hit performance issues, that might be an improvement, like throwing away inactive states in the next cycle, because we can assume that everything that's not in the map is inactive. But let's try to parse our input. See where that takes us. That looks correct enough. Never assume, I've learned in Advent of Code Puzzle. So it's first thing is active, and then we have inactive, and the next row starts with active and inactive again. So rows and columns. I'm gonna draw this because this trips me up every time. It's important enough to have somewhere in sight. Let's get our drawing pad out. I even have like my drawing apparatus next to me, so let's use that. All this preparation. Oh, come on. If my apparatus works at least. There we go. Look for the app here. I don't know what you use for online note-taking and sharing a whiteboard with people, but Miro, I love it. Especially in my day job where I write software for a living. Having an interactive drawing and a note post-it tool, it's amazing. But we're digressing. Oh, that's a very fat line. Let's trim that down a bit. So yeah. Z is, yeah, C will go somewhere here, but X is this way, Y is this way. Yeah, let's keep the original. Let's keep it Advent of Code original, and let's have our Y go down. Okay, I'm gonna keep this inside somewhere, and let's have Z drop somewhere. Z doesn't matter because we'll only be thinking it in the abstract sense. But what was I trying to see? Oh yeah, if our input gets parsed correctly, so we're expecting 0, 0. This is 0, 0, right? Yeah, that's 0, 0 to be active. And then 0, 1 to be inactive. Interesting. 0, isn't this like, appears to be this. Eh? What am I doing wrong? Let's do it, let's try to parse a smaller example. It'll be easier. Yeah, so a dot, and a dot Twitter. There we go. So what are we calling it? 0, 0 and 1, 0. Oh yeah, I was confused again. Are inactive, yeah, and then we drop, so it's blop 1 and 1, 1 should be active. Yeah, I think I was just getting confused. Yeah, let's anyway just try the example in a second to make double sure. Okay, continuing, we have our let's explicitly type this because we put effort into giving it a type alias. So now we can parse pocket dimensions. Next interesting step maybe is to write the function to calculate the next cycle. So let's name this next cycle maybe, given a dimension. Dimension is maybe a tricky word because we are also using three-dimensional grids or a three-dimensional coordinate system. But anyway. So we need to loop over every... oh yeah. I'm remembering something. I am not using a three-dimensional matrix, but actually we don't only need to look at the known dots in our map, because what am I trying to say? A neighbor of something like on the edge of this three-dimensional blob could also like come alive maybe. So let's look at the rules. If a cube is active, no, then it's already in our map, so cool. If a cube is inactive, but exactly 3 of its neighbors are active, yes, and that could happen to a point that is not in our map already, then the cube becomes active. So when we start looking for all the cubes we need to do work for or potential work for, it's not only the things in our map, it could be things in our map and beyond. Okay, this might not scale as well as I initially thought. Okay, but let's do that first. So yeah, okay, so this is the... Let's explicitly type this as well. We get a pocket dimension, return a pocket dimension. And now we're looking for what are the things we need to do work for. What's the problem here? A key value pair is not a sequence, are you kidding me? Okay then. Or it's not a tuple. It's a map, and I can't do sequence.map on it? Okay, I was thinking maybe I could. Let's do it this way then. Or actually we can do keys. No? We cannot do keys? Give me all the keys? No, okay. So be it. So these are all the keys. It could be that we need to look towards the edge surrounding our current universe. So let's call a new function. Candidates for a dimension. Yeah, let's do it that way. So let's write a candidate generating function. Which is doing what we're trying to do here. Oh, that's one too many. Yeah. So this is what we were trying to do. Let's get all the coordinates out there. There we go. And let's add some boundaries. How do we calculate the boundaries? It's not a problem if we take too much work on. It is a problem if we leave some out. My brain is starting to hurt thinking about 3 dimensions. What do we need? It would be nice if we had like an idea of the edges of our current universe. We can derive that from this. Is that good enough? What happens if we take the smallest x, the biggest x, and do that for every 3 dimensions? That will not be good enough. What happens if we take the neighbors, like all the 26 neighbors from every point. I think that works. Yeah, because all the rules work on neighbors. So if we are looking for candidates that potentially change their cube state, it's always on neighbors. So if we are looking for, okay, for which points in the cube do we need to, or in the 3D grid, do we need to do some work? If we just like generate all the neighbors from every point we know, then we definitely have every coordinate we need to do work for. It will be overkill, but it's not a problem. So instead of beginning with the candidate generating function, let's begin with the neighbors function. So neighbors given a dimension and a coordinate gives us all the neighbors. In 2D I did it by generating all the offsets and then just applying them. I think we can do this here. It's 26, right? Yeah, it's 26 potential neighbors. Or not even potential. In an infinite space there will always be 26 neighboring spaces. I like how this is scaling up from one of the previous days where we did a easy finite grid, and now it's a bit more interesting. Let's see how we do this. I'm gonna do the 2D approach and see if we can take it from there. So let's forget about the z coordinate for now. So this is yeah, this is top left. So if we're at the center, or if we're at the origin, this is top left above us. What's like directly above us, this means the y coordinate is changing. So it would be something like this. Are we still in line with my doodle? If y grows, we're going up. No, if y shrinks, we're going up. Yeah, that's correct. Okay, let's keep it this way then. It doesn't really matter. If we generate all the valids, it doesn't even matter. Like, we don't need to know if we're going up or down. We just need to know we're doing both. So this is the row above us in the 2D plane. Let's do a row that is ourselves, or like our current row. So what's the row? The y stays the same, so y is always 0 here. Yep, looks correct. And now you'll see that our current element is in there, but that's not correct if we're looking for neighbors. I will be keeping it in there because I'm thinking about how we'll handle the 3D case. There we go. So this is 1, 1, 1. And so this is all the neighbors, including ourselves, in the current plane. And then we need to go 1 z coordinate up and down. So it's actually this. And for every offset, let's generate the 2 other z coordinates. So let's call this x offset, y offset, z offset. And let's do x offset, y offset 1. Yeah, we don't need a z because it's always 0. Bye-bye. Or actually, let's do that here. Yeah, we didn't need the z's in this grid actually. Let me get rid of it so it's clear that this is not necessary here. Otherwise, people might look at this and say, why is there a 0 here and you're throwing it away here? So we have like all the neighbors in our current plane, including ourselves, and then we say, okay, so like every neighbor is this, and this, and this. 0, no, oh, offset, -1. So these are all 27, yeah, coordinates. And if we just do a, oh, by the way, we will not be using ourselves because we're not a neighbor of ourselves. I think this generates all the, is except working on the list, yes. I think this is good enough to generate on neighbors. Let's give it a try. Do we have a 3D space somewhere? We have now. Learn to type. There we go. So let's try to do candidates of this pocket dimension. And let's try to find the candidates of something, doesn't matter. Eh, what are you saying? Candidates takes a map and a C list. That's not correct. Neighbors, sorry. So let's see what we get. Expecting there to be, what was it again? 26. Yeah, looks correct. Let's take a look at the numbers. That's actually a bad example. Let's do 10, 10, 10. Then we can see what's actually happening with the numbers. Oh yeah, that's not correct. Good thing we catch this now. We're calculating the offsets, but not the actual coordinates. So, yeah, so except 0, 0, 0, actually. Yeah. And now let's calculate the full coordinates out of this. Do it this way. So x offset, y offset, z offset. Could have done this here, but yeah, okay. And now let's do x plus the offset, y plus the offset, z plus the offset. So now we do have the absolute coordinates and not just the ones relative to the point we provide. That looks correct. Let's maybe even try a distinct and see that we still have 26, and then I'm happy. Yeah, we're good, I guess. So we took a detour into neighborland because I realized that it's also interesting to have neighbors when you try to calculate candidates. Because if we take the current known world and we calculate the neighbors for every point in our world, so if we calculate the neighbors given this current dimension, and if we paste on the candidates themselves, yep, then we have our potential points that could be affected this cycle. And for good measure, I don't know if this can happen. Yeah, it can happen. Let's not do too much double work, and let's distinct it. So I think now we know for which points we potentially have to do work. And now it's just a matter of doing the work for every candidate, which is applying these rules. And we already have the neighbor function, so I think we're almost done for part 1 at least. So we have our candidates. Let's do something for every candidate. Yes, let's do something for every candidate. Let's use a fold so we can thread. No, can we use a fold? No, let's not use a fold because it all has to happen at the same cycle. we don't have to do things incrementally. Changing one candidate should not affect subsequent candidates. So I think we can just map the candidates to something called, I don't know, apply. Yeah, so apply rules given this current dimension or this state of the world. So then we know for this candidate what would happen, like what's the next state. So let's make an apply rules dimension candidate. We also kind of need to know so this is a coordinate. We kind of need to know the state, right? Yeah, if a cube is active or inactive. Yeah, that's not a problem. So let's just give it the candidate. Yep. And let's have this return an entry in our pocket dimension, so a coordinate and a cube state. So candidate and, for example, active. So this generates the new states for every candidate, and now we can update the map. So let's call this updates. And now we can fold, right? Yeah, everything has been calculated. So now we can do dimension map at an update is a sequence of coordinates and cube states. So this is a coordinate and a cube state, coordinate and a state. So map at coordinate this state given our initial dimension. What's not working? Okay, everything is working. So I think this is it. We only need to write the rules. And are those still in my copy paste buffer? Yeah, they are. So if a cube is active, what was candidate again? Already forgot. Coordinates. So let's look up the candidate first. Is it always there? No. Okay, I'm gonna extract the is it always there part. Am I going to extract the always there part? Yeah. So let's what's it called? State at, yeah, state at, given a dimension and a coordinate is a dimension. Let's try to look it up. So let's try to find coordinates. Let's pattern match on the result, or let's not pattern match on the result. So this can fail. If it doesn't fail, we can, oh yeah, let's pattern match first. I'm not sure what to do, so then I always drop back to the thing that I know works, not the thing that I know that should work, but I have no idea how to do it. So if we find a state, then we're done. If we don't find a state, then we make the assumption that everything is inactive, right, at the beginning. Yeah, all cubes start inactive. Yeah, and if you see this, like if you find some, do this, and otherwise, if you don't find anything, there's a default. There's something called I think it's this default value. So you give it a default value and an option and return of t. Yeah, I think this is it. So I'm doing a refactoring, but I'm doing a bad job at explaining it. So this is pattern matching on the try find, and if we find some, we return something, and if we find nothing, we return a default. And this is exactly what option default value does. So this is the default value. and then it needs an option, right? Yeah, and that's actually just our try find. So I think this is identical. There we go. And let's give that a try. So we have our pocket dimension here. Let's try to find the state at the origin. Which is active, is that correct? Yes. And if we try to find something at whatever we don't have, so this doesn't exist, that should be inactive. Okay, it works. Or I feel comfortable enough. Now we can do the actual rules. If a cube is active and exactly 2 or 3 of its neighbors are also active. So let's find the number of active neighbors. So this is the cube state. We need to find the neighbors again. We're doing a lot of neighbor calculations, but okay, for 6 ticks it's not a problem. Neighbors is the neighbors given the dimension and a coordinate. So these are all its neighbors, all 26 of them. And we need to look up the state for each of them. What's it called? State at, given the dimension. So these are the state, neighbor states. And we need to know how many active neighbors there are. So these are the give me the neighbors, get their state, and let's filter them. Can I do a count by them being active? I don't know if I can do this shorter actually, but doesn't really matter. Let's keep on going and let's look up stuff when we're done. So this is how many active neighbors we have. And now I think a simple pattern match will suffice. So match the current cube state and the number of active neighbors. So this is the number of active neighbors. Okay, so now we can do a literal transcription of the rules. If a cube is active and exactly 2 or 3 of its neighbors are active. Can I do an OR here? Probably. Then the cube remains active. So let's call this thing next state. So if cube is active and we have 2 or 3 active neighbors, active. Otherwise, if we are active and we have a different amount, we are inactive. Why am I seeing red squiggles? What's the problem? Because we need to call the actual map find. Okay, I was a bit in the woods here. So this is the first rule. Otherwise the cube becomes inactive, yes. If a cube is inactive but exactly 3 of its neighbors are active, so that's this case, the cube becomes active, and otherwise the cube remains inactive. What's our compiler warning us about? Okay, so that's not actually what we need. So let's just say in every other case. No, this would catch it as well. So in every other case, don't care, we remain inactive, right? Cube remains inactive. Yes. So this English description can go. We have code, which is like impossible. No ambiguity here. I think we're done. So let's try to run a cycle. We have our input. Let's try to run a single cycle on it. Come on, you know you want to. Oh, interesting. Key not found. We're doing a map.find. We're doing a map.find. I thought we were doing map.try-finds here. 150. I would love to see an error line 61, somewhere around there. Where is the map.find? This is not nearly line 61, this REPL thing. Okay, but we're doing a map find. Yeah, so we always need to be... why am I doing this and not state at? I was doing an extract method, but I forgot to finish the refactoring. Okay, this will work better, I'm thinking. There we go. Better. Muchos better. And now we can do this 6 times, I guess. We don't even need to write an infinitely generating ticker. Let's just do it 6 times. So this is initial, this is after 1 tick. 2, 3, 4, 5, 6. Here we go. Oh, that was actually slower than I thought for only 6 ticks. Oh boy, I wrote some non-performing code today. How many cubes are left in the active state after the 6th cycle? So let's do that slow thing again, and let's count the number of active. $252. Jesus, this universe grows fast. After 6 ticks, we have like 252 active states in there already. Yeah, this will not work for part 2 probably. Interesting. How long have we been going? 40 minutes? Okay, let's continue on for a bit. Now, interesting, our simulation doesn't match reality. Haha, thank you, Eric. We don't have 3 dimensions, we have 4 dimensions. This is like, we use Game of Life, or the puzzle, the grid with cells changing, and we use that at programming exercises as well. And like having growing number of dimensions is one of the things we play with over there as well. So it's not the first time I see this constraint or this added challenge, but it's pretty impactful on your code if you didn't see this coming. So yeah, we're going to lift this up into 4 dimensions now. X, Y, Z, W. So we're calling them hypercubes now. Cool. So even the domain changes. Each cube only ever considered as neighbors. Any of the 80 other cubes. Oh boy, oh boy, oh boy. Yeah, let's try it. I think I'm gonna hit a performance wall and I'll start to stumble through, but then I'll just cut the stream and we'll take it from there. Any of the 80 other cubes where any of their coordinates differ by at most 1. So our approach, that's basically what we've been doing, right? But I don't really know how to scale that to 4 dimensions. Interesting. Oh my god, if a single point has 80 neighbors, how many cycles do we need? Oh, only 6. So it'll what? Scale? Yeah, it'll be worse than the part 1, but it'll actually, if we only need to calculate 6 ticks, that's not the end of the world, I'm guessing. So we still get a small 2-dimensional input. Same rules apply, only now we're working with 4D space. And then we have an example again. So actually, yeah, the only thing that will change, or like the only thing that will change, is we add a 4th dimension. And this will definitely have impact on the looking for neighbors. Because we needed 80? Yes, we'll find 80. 81. I can't imagine 4D space. We're not built for stuff like that, so yeah, let's just try it out. Let's just try it out. What is the impact on our code if we change to 4D space? Yep, let's make the assumption that our input starts at W, or the W axis on 0 as well. Our pocket dimension will grow. So yeah, this is quite an impactful change. There we go. This will be the, I think this will be the hardest part. Now we need to find not the 26 neighbors, but all 80 neighbors. Yeah, okay. How will we do this? Maybe change tactics a bit. So we need to do +1, -1, and 0 of all 4 axes, right? That's a bit the hint this part was pointing out. So you need to find 80 surrounding cubes where any of their coordinates differ by at most 1. And in 2D it was nice to like list the deltas, and in 3D this scaled if we did this little hack, but in 4D also this will probably work if we just do another step of collecting and appending a W. Yeah, actually I think that might work. Now we have 27, and if we do that times 3, 60 and 21 is 81. Yeah, that will work. So now we're working in 3D space. Let's lift this to 4D space. So X offset, Y offset, Z offset. And now we just do the same. So one where the W is 0, one where the W is 1, and one where the W is -1. Except the point of origin, yeah. Okay, it's not that terrible, or changing the code is not that terrible. Running the code, that will be a bit more interesting. Let's first try to check a bit, let's check a couple of properties of a neighbor function. So now we have 4D space, yes. Let's try to find a couple of neighbors. So it should be what? 80? Yep. Let's just manually inspect them for a while. Does that look? Yeah, that looks somewhat like what we expect. And let's try to find our original. It should not be in there, like the coordinate itself is not a neighbor of itself. Yep, that's true. Okay, so I think this is the neighbor function. And if I'm reading, or if my F# compiler is correct, that was the only change. Oh, it's not that bad. But now, the big performance question. Will this blow up my CPU? let's not do that just yet. Let's give it some feedback. So every time we start a cycle, let's print something. Let's break with every purity advice we have, because we're being pragmatic here. So let's just print something out every time we start a new cycle. Still 6, we still need to do 6, and yeah. So, oh, actually it's not the end of the world. I think if we clean up, if maybe we clean up some intermediary dimensions, like throw away everything that's inactive, stuff like that, we might even 1, 2, 3, 4, 5, while we're almost there. We're calculating the 6th and final cycle now. I hear my laptop like take flight. It's lifting off. Oh no, don't let step 6 be the one where it'll take a subordinate amount of time. This is growing exponentially. Oh, there we go. No performance tweaks necessary. There we go. Yay, we did it. Will we do the performance tweak? Yeah, we have 10 minutes left before the hour. Let's look at how fast this works. Let's maybe time it first. And so let's put on a performance timing for dummies. Kind of do-it-yourself performance measurement framework. There we go. And let's do that calculation again. And let's think about how we can get this faster. The only like naive thing I can think of is at the end of a cycle, just throw away all the inactive states from the map. So it only takes it only keeps track of the active ones. So this is a bit more memory. It's easier on memory. Is it easier on computation? I don't know, because then we still look it up in the map. If we don't find something, we just say inactive by default. We will have less neighbors to like loop over when we calculate candidates. Maybe that's where the big win is. We won't have as much candidates in going dimensions. So right now it's taking 46 seconds for part 2, which is quite a bit. Let's try our naive performance tweak. So let's do updated. Wait a second. So these are all the updates. Yeah. So this is our updated map. Are we really going to convert this map back to a sequence so we can throw stuff out? Yeah, let's try it. So I don't know if you can do something with a map filter. Oh, you can do map.filter. That's exactly what we need, right? Yeah, that's exactly what we need. Cool. So only keep the active key value pairs. So what are you saying? So you need a predicate that takes a key and a value and returns a bool. And you, oh yeah, updates is not what we need. Updated. Next, let's call this next. So we just do the same as we did before, but we throw away everything that is not active. Let's see how this impacts our performance. That's faster, right? Still not a lot, faster, but 7 seconds in F# using nothing but immutable data structures. I am happy. Is the end result still the same? Yes, it is. So I am happy. I even have a reasonably fast algorithm, and my personal constraint of using immutable data only has been, it worked today. So happy camper, happy little Christmas elf here. Hope you had fun solving this puzzle with me, and I'll see you tomorrow. Goodbye.